Okay, in this video we're going to be looking at examples that are in my notes, some of which we've spent a little bit of time with, some of which we haven't, but it won't hurt to review some of these. So the first example is the log being pulled up the hill, being pulled down by a weight. We're going to go through this one very quickly because we've already talked about it and thought about it in class. Okay, the problem statement gives some of the details. A 250-pound concrete block is released. It pulls the 400-pound log up the ramp. We have coefficient of kinetic friction, 0.5. We want to know the velocity when the block hits the ground at a distance of 20 feet below. And so to work the problem, we will need to draw free body diagrams and write sum of force type of equations. Now, looking at the complete system, of course we do have the log right here. We have a block and tackle or a pulley system, and so we do need to understand how the tension forces in the rope are distributed. And so what I would say is I have 1 T in that rope there, and I've got tension in the rope as it comes over, and I've got tension in the rope as it comes around. And so we've got 2 T on this side, and since the pulley is massless, there is 2 T acting on that side. And so we'll draw free body diagrams, and we will cut the rope for each one of those free bodies. Free body means only one body, and so for the log, first of all, we will make a choice to align our coordinate system with the slope, where y points away from the slope. We have chosen x pointing down the slope, and I already talked about in class that makes sense when we consider that we have chosen SC pointing down the slope as positive when we're going to write our kinematic equations here, and SA is pointing downward here. So on our block, our positive coordinate direction is going to be pointing down. And so the equations we'll be able to write here will be sum of forces in the y direction equal mass times acceleration, but there is no acceleration in the y direction, so that'll give us a relationship between the weight and the normal force, and that'll tell us the friction force. Sum of forces in the x will be important. Sum of forces in the y will be important. And also our rope equation. Our rope equation here would be an SA plus a 2SC is equal to a rope length. So let's look at the equations that fall out of all of this. 0 equal 2AC, 2 acceleration of C plus the acceleration of A. We've already taken 2 derivatives to get to that. So that's one equation and 2 unknowns. AC, A, both showing up as unknowns for the first time. I can't find a good pen here. Let me try again, and we'll see what happens next time. And then from the log in the y direction, sum of forces in the y direction is equal to the normal force positive, 400 cosine of the 30-degree slope acting downward equals 0. That tells us the normal is 346, and that's going to tell us what our friction is. And then we sum forces in the x direction equal mass times acceleration in the x. We have the normal force times coefficient of friction in the positive x direction. We have 2t in the negative x direction from our free body diagram. We have the gravity term in the downhill component of the gravity term of 400 times the sine of 30 degrees is equal to mass, 400 over 32.2, times the acceleration. This equation has 2 unknowns, tension and the acceleration of C. Tension is new. Acceleration of C we had previously, but we are at 3 unknowns at this point with 2 equations, so we are going to need another equation. And so we turn to our block and write sum of forces in the y direction, where y is positive downward, equal mass times acceleration. And so we have the weight force acting downward, that's positive. We have the tension force acting upward, that would be a negative. And then the mass is 250 over 32.2 times the acceleration of A. Tension and acceleration of A are the unknowns in this one, but they're not new. We now have 3 equations, 3 unknowns. Solve them. And the key thing is now we know the acceleration of block A, and it is a constant. I did mention in class that it shows up positive. That does fit with what we expected the problem to do. And now we can take that constant acceleration and find the velocity change when it drops a total of 20 feet using the ADS equal VdV form of constant acceleration. Here it is. There's the answer. We had already talked about that problem, so I'm going to let that go right there.